So we've seen that massive stars, when they run out of their nuclear fuel, they collapse down and form a supernovae, and in that process leave a neutron star behind. An incredibly dense ball of neutrons, about 10 kilometers, even less across, but more than the mass of the sun, where gravity is as extreme as you can possibly imagine. And there are literally hundreds of millions of these things scattered around our Milky Way, and we see them as glowing hot balls that emit in the X-rays or even gamma rays sometimes. And we also see them as these peculiar pinging radio objects we call pulsars. They really are remarkable objects.
And the study of them is still ongoing, but in many ways their biggest use now is not for studying themselves, but because of what they can tell us about other things. Particularly these pulsars that spin very fast. Remember that when they first form, they're spinning at maybe once a second, but they have very strong magnetic field and they slow down fast. After a while, they lose most of the magnetic field, but they're probably drifting off somewhere deep in space. But if they're in a binary, as we've just talked about, they can get more mass dumped on them, they can spin them back up. And some of these things are spinning only at millisecond periods, like 1,000 times a second. And they're called millisecond pulsars, curiously enough. And these turn out to be fantastically accurate clocks. These pulses, which maybe 1,000 times a second, are better than any clocks we can measure on Earth.
Well, actually, Paul, it turns out humanity has finally gotten one step up in front of those pulsars for accuracy. It appears we finally are able to beat pulsars with the best new atomic clocks and through really precise measurements. So they are amazing atomic clocks. And imagine being able to put atomic clocks around the galaxy. Think of all the interesting physics you could do.
We've already talked about one thing in the exoplanets course, the fact that because they're sending their pulse out so precisely, if one of them has a planet around it, that causes it to wobble backwards and forwards, not by very much, we're only talking meters here, but that can be measured with such exquisite precision that they can find very low mass planets around these things. We talked about that in the last part of this course. But perhaps even more exciting is the use of these things to probe the physics of strong gravity. There's another Nobel Prize, of course, in this.
Yeah, that's right. So Holst and Taylor discovered a binary pulsar. That is, two pulsars going around each other, where you could go through and see the one pulsar that was easiest to see and use it to time what's going on. And it turns out there's all sorts of interesting relativistic effects, general relativistic effects, that is, things that only Einstein's gravity predicts. And one of the things is gravitational radiation. So as one neutron star goes around the other, it will let off gravitational radiation, and that will cause its orbit to essentially get closer and closer to the other object over time. So the whole thing will essentially speed up a little bit over time. And that was seen, and general relativity predicted exactly what was seen in this binary pulsar, and led eventually to the 1993 Nobel Prize.
Yes, of course, general relativity is normally very hard to test on Earth because the gravity just isn't strong enough. If you had a black hole in our lab, it would be pretty easy, but luckily we don't. So these neutron star binaries are one of the few places where you can actually test this theory, and so far it's come up with flying colours in these extreme environments.
And one of the other things is that there you're inferring the existence of gravitational waves because you're seeing essentially the energy that's left the system.
It must be going somewhere.
That's right. But these same objects, because they're amazing atomic clocks, give us the opportunity to maybe directly detect gravity waves. So imagine you see two objects orbiting each other, letting out gravity waves. Those waves cause space to do that. And when space gets bigger and smaller, if it's bigger, then it takes longer for example, the radio waves to get through that part of space. And if it's shorter, it's quicker to get through that part of space. So imagine you have really big gravity waves, that are billions of kilometers across. Then if I look that direction at a set of pulsars and compare it to a set of pulsars that direction, I'll suddenly see that those pulsars will slow down. Well, these stay the same speed, and then eventually those might slow down or speed up. And that would be be a way to detect space sort of stretching and contracting due to gravity waves.
So the race is on to discover gravity waves at the moment. They've been inferred from microwave background observations and from the pulsar measurements, but never directly measured. There are labs around the world trying to measure it, and they're getting pretty close now. But maybe the astronomers will get there first and discover them via this effect on the radiation coming from pulsars.
Right, so pulsars really are one of the great toolboxes that astronomers have. There's literally been 3 sets of Nobel Prizes now related to them. And so the interesting thing is there anything even more interesting than neutron stars? And many of my colleagues who study them say no.
Yes, so we've started with white dwarfs, and they're pretty violent, but neutron stars put them in the shade. What could come worse? Well, we know that the neutron star is held up by neutron degeneracy pressure, and that's a lot stronger than electron degeneracy pressure that holds up white dwarfs, because neutrons are a lot more massive. Therefore, they have a lot more energy before they get close to the speed of light, and there's going to be a limit then. Eventually, if you pile enough mass on a neutron star, it's going to do the same. It's going to hit its own Chandrasekhar limit, do the same thing that a white dwarf does, and collapse. And then what happens then? Well, that's a topic for our next video.